Y'all doing okay today? Yeah.
Doing good. How are you?
What's that?
So doing all right. How are you?
Oh, okay. I thought you said I need to get a haircut.
Yeah, I do actually. Yeah.
I need one bad. That's why I keep wearing a hat. Anyway, let's see. We got another minute. Oh, here we go. 11 o'clock. All right. So last time we started with trig integrals, and I showed you in the formula sheet that there are sets of steps that we can use to assist us with trig integrals. But one thing that we're going to see today is that these steps, these procedures don't always work. I mean, sometimes it's something else. So we want to try, when we see a trig integral, to go to these things, go to these notes, but let's not think that everything can be done with this. If that were the case, then I would tell you that right off the bat. Be like, okay, if you see a trig integral, just follow these steps and you'll be good. But you'll see when we get to some other examples, things get weird as expected. Okay, so we're going to start off with this trig integral. We want to find the antiderivative of sine squared x cosine to the 5th x dx. You know, initially you might think just a basic u substitution would work here. You know, you have sine, you have cosine. So, you know, if you let u be sine x, we have the derivative, right? Cosine, but it's raised to the 5th power, which is not necessarily a good thing. If we do it the other way around, we let u be cosine x. The derivative of that is negative sine x. We have a sine x, but it's being squared. So again, that's kind of an issue. What I'm getting at is if it was just cosine x here, no 5 on that, then we would just do a basic u sub. U is sine x, we'd be in business. But we don't have that. So let's go to the steps here. The first thing, when we're trying to integrate powers of sine and cosine, first we look, is our cosine odd? Well, in this case, our cosine is odd, right? We have an odd power of cosine. So we are going to work with this and see what happens. What we're supposed to do is save one factor of save one cosine factor. And so what that means for us is we're just going to factor out a single cosine. So we're just rewriting the problem. Instead of cosine to the 5th, we're now going to have cosine to the 4th. And here's where we have essentially peeled off a single factor of cosine. And the whole idea behind that peeling off of the cosine is that that part in blue is now going to be the du that we get when we do a basic u substitution. So we kind of already know that the du, we want it to be that part in blue. All right? That means our u would have to be what? In order for the du.
Sine.
I'm sorry?
Sine.
Sine, right? That means u would have to be sine. And that's what it says in the steps here. We're going to make a substitution that u is sine, right? That's what it says in the steps. But I want us to be thinking about why. The reason is because that blue part is going to be the derivative. Now, the one issue we have right now is that, of course, we've got a sine here, so we'll be able to replace that with u. Let me go ahead and write u as sine x. And let's go ahead and write du, which is cosine x dx. The part in the green is fine, right? Because that's sine, that's going to be replaced with u, and we're happy. The trouble part, or the part that we still have to address, is the fact that we have a cosine x there, and that needs to somehow be switched over to sine. And we're going to use the Pythagorean identity, our trusty sine squared x plus cosine squared x equals 1, and solve that for cosine squared. And that's where this part of the notes comes from. They're just taking that and solving it for cosine squared. So we're going to replace anywhere we see cosine squared x, we're going to replace it with 1 minus sine squared x. Problem is we don't have cosine squared. We have cosine to the fourth. And that means we're going to have to do something else. We're going to have to rewrite cosine to the fourth as cosine squared squared. And that's just so we can make the substitution, right? And I believe I mentioned last class that this formula up here, it does not, you can't just replace that with any number you want, okay? That doesn't work. It can only be squared squared on the two trig functions. So unfortunately, we have to do this step where we do cosine squared squared. Now though, we can replace the cosine squared x with 1 minus sine squared x. Are there any questions while I'm writing this? We're good. And at this point, everything matches up. We've got the cosine x dx. We know that that's du. We've got a sine squared x here. We've got a sine squared x here. The sines will be replaced with u's. And so now we can rewrite the integral. So let's see. Today, we'll start with Jorge.
Yes, sir.
Jorge. I heard you.
Yeah, I'm right here.
Okay. Jorge, so are you with us here?
Yeah, I'm already, yeah, I'm
Okay, so what's the new integral in terms of u?
The new integral in terms of u will be u squared,
Okay.
parentheses, 1 minus u squared, and parentheses, squared du.
Good. Now, how are you going to deal with that integral? Do you have an idea of how you can approach that one?
First, you would read 1 minus u squared.
Okay, so you're just going to go ahead and square this out on the side like some scratch work?
Yes, sir.
Okay, and I'll just do that, trusting that we can all get this. So if you FOIL it out and collect like terms, all right, and then Jorge, what now?
Then you put it back in the parentheses, then you distribute the u squared into that.
Good. So we still have that u squared out front that's going to have to come through. And this is all good, right? Like we're happy to see this. This is just going to be power rule when we're done. We're basically looking at a polynomial function, which is just a bunch of powers of u, and we should be able to integrate those term by term. Jorge, you want to keep going?
Yeah, what I got after that was 1 over 3 u cubed
U cubed.
minus 2 over 5 u fifth
Okay.
plus 1 over 7 u 7.
Good. Okay. And then we have one additional step, right?
Mm-hmm.
Replace u with what it was, and it was sine, right? So it's going to be sine cubed x minus 2/5 sine to the 5th x plus 1/7 sine to the 7th x plus c. We're done. Okay, so that I think that worked out pretty well for us. Would you agree? I mean, we peeled off the cosine, we rewrote the other cosine that was still there in terms of sine, and then turned it into a polynomial, expanded things out, power rule on each one, substitute sine back in, we're done. Any questions? All right, let's take a look at the next problem that I'd like to do. So on our notes, I did something like A here. I did a sine cubed 4t, and I believe I did a sine to the 4th. So let me just go back in the notes from last time. I think the last problem I did, yeah, we did a sine to the 4th x. So I think that problem there, if you go back and revisit this, we had to do something else here. We had to use the half angle identity instead of the Pythagorean identity. And, you know, that's all stated in these notes here. You know, if we had an even power of sine and cosine, we've got to use this step. So what I'm getting at is I've kind of done these examples. I didn't do the one with beta in it. So I would suggest you go back and try and do this problem with the beta, because you got to kind of keep track of the beta the whole time. And just so you have it, let me see. My Tuesday, Thursday class, I believe, oh wait, that was last time. Yeah, this is that problem. I'm just going to put it up on the screen, so if you want to come back and look at this, you can on the video. This is the solution to that problem. So there's the first part, and then there's the end. So just so you have it on record, there's that problem worked out. Okay, we need to continue to move on through this section. So we've established, I guess, a technique to attack trig integrals, right, with sine and cosine in them. Now we shift gears and we try and do trig integrals that have tangent and secant in them. And there's some things that we need to know going into this. You know how on the previous problems, what we were doing was like the one we just did, we peeled off the cosine. And we peeled off the cosine because cosine was the derivative of sine. And then we rewrote everything else in terms of sine. Here, with tangent and secant, it doesn't work as nicely, because if we ever have to peel something off, it's either going to have to be that we peel off a secant squared or we peel off a secant tangent, because the relationships that we have are a little different with tangent and secant. We know that the antiderivative of secant squared is tangent, and we know that the antiderivative of secant times tangent is secant. So again, this goes back to Cal 1. We know the other direction in Cal 1, right? Derivative of tangent is secant squared, derivative of secant is secant tangent. So we're going to need to know that before we can do this technique. We just need to remember that those two antiderivatives, we know them. And then this next part is just to remember that if you throw an a in front, that you're going to have to scale that out, right? If you have a linear expression inside the argument, you just have to scale it out. So that's all that's about. Let's get into the technique. So there are a set of steps. These steps, I've written them down here, but they're also going to be here on the side while we do this next problem. These are the steps. These are the ones that are in your formula sheets. So I will just throw it in here. Okay, and we will follow that when we do this first example. So first example is tangent to the fourth x times secant to the fourth x. Let's go after that one. All right, so we have to look at this. We have to realize, okay, we've got a trig integral. I don't see anything obvious. In other words, I don't see like a basic u substitution, something in its derivative. How about if that secant to the fourth was just a secant squared? And couldn't we just make a basic u substitution? U is tangent, and then the derivative of that is just secant squared, and we'd basically be there, wouldn't we? We wouldn't have to do anything else. But that's not what we have. We have secant to the fourth. So we go over here and we start reading what we've got. Okay, first thing, if the power of secant is even, then we're gonna do something. Well, that's what we have, right? We have this. This power on the secant is even. So let's follow through the steps. What we're gonna do is save a factor of secant squared. So just like we peeled a cosine off in the previous problem, now we're gonna peel off a secant squared. So let's do that. Let's just algebraically rewrite this. We're gonna have tangent to the fourth x. We're peeling off one of the secant squared. Well, we're peeling off two factors of secant. We started with four factors, so there's our peel off right here. Now that's gonna be the derivative, right? We're thinking ahead. That's gonna be our du. So what is u gonna have to be?
Tangent.
Tangent, right? Now it says it in the notes, but again, there's a difference between just following something and understanding what you're doing. So I know over here that I'm going to make a substitution that u is going to be tangent x, and the derivative of that is secant squared x dx, and that's what I peeled off. That's why I peeled it off. So I could see du right there. And we're going to replace tangent with u. So just like the problem before, we still need to resolve the secant squared. We got to get rid of that secant squared. And we've got to use the Pythagorean identity in order to rewrite that in terms of tangent. So the other Pythagorean identity, it's written here, but I'm just going to write it up here so that we all can look at it by itself. this identity, right, is one of the 3 Pythagorean identities. Everyone knows sine squared x plus cosine squared x equals 1, but there are 2 others that you should be aware of, and this is one of them. So that identity is already solved for secant squared. So that's great. We just replace that secant squared with 1 plus tangent squared. So I'm just going to rewrite tangent to the 4th. Any questions while I'm writing? Still have secant squared. There we go. All right, how about Cheyenne? Is Cheyenne around? Cheyenne. I don't see Cheyenne. Okay, how about Ross? I know Ross is here. I saw Ross. Where's Ross? Hmm?
I'm here.
Okay, there you are. I put in a request. There's actually a lot of people who put in a request to Zoom to be able to organize your videos like alphabetically or something, because y'all are constantly moving around. Like, you know, 1 minute you're over in one corner and the next minute you're on a different line. I don't know how it is on your end, but on my end, that's the way it looks. So
Yeah, sometimes that happens.
yeah. Okay, Ross. So you with this up to this point? Are you good?
Yes, sir.
Comfortable? Okay. So how would this integral be transformed now?
So we then make it the integral of u to the 4th,
Mm-hmm.
and then parentheses 1 plus u squared,
Yep.
parentheses du.
Du. There we go. And then how do you want to handle that?
You make it u to the 5th plus u to the 6th du.
Oh, that right there is just u to the 4th, right?
Oh yeah, u to the 4th, my bad.
Okay. U to the 4th plus u to the 6th. So you're just distributing the u to the 4th through.
Yeah,
Yeah.
I just forgot the word distribute.
Yeah. I was thinking, when I asked you, I was wondering what word you were going to use.
Yeah. It's already been a long morning, so
Well, I hear you now.
yeah.
You knew what to do. All right. So now at this point, what do we got, Ross?
Well, at this point we can integrate it, so then it becomes 1/5 times u to the 5th plus 1/7 times u to the 7th.
Yep.
Plus c.
There we go. And then just replace the u's, right?
Mm-hmm.
And we'll just do the tangents in there. And we will be done. There we go. Do y'all like the ambient bird noises in the background? Isn't that peaceful? Isn't that very peaceful? German, is that you? You can leave it on. I'm okay with it. I feel a Zen moment here. Okay, this is good, right? Any questions? All right, so let's look at another one. Let's do tangent to the 5th x secant cubed x. Tangent to the 5th secant cubed. In my other class, I had a student ask me, you know, can you use this method where, you know, where it said like if secant is even, can you still use that even though that 3 is not even? Like, can you still peel off a secant squared? And you can peel off a secant squared, but you'd be stuck. And I just want to show you why you'd be stuck. If you peel off a secant squared, you're going to be left with secant x, secant squared x, dx. And this part here is your du. Everything else has to be rewritten in terms of tangent now. But the problem is you don't have a way to convert the secant x to a tangent because you don't have the Pythagorean identity anymore because the secant's not squared. And there is no direct formula or equation that we have that connects secant to tangent. So there's no easy way to get rid of that secant. So even though you could peel off the secant squared, you're going to get stuck, which is why the steps tell you what to do here, right? The steps tell you If you've got an even, you do one thing. Well, we don't have an even. And it says here, if the tangent is odd, now we have it in an odd tangent, don't we? If the tangent is odd, then we're gonna factor out a secant tangent. That means we're going to peel off a secant and a tangent. So let's peel off a secant and a tangent. So we rewrite tangent, I'm peeling one off, so I have tangent to the fourth. I have secant cubed, I'm gonna peel one of the secants off, and I'll put that over here on the side. Here's the secant I peeled, here's the tangent that I peeled, and then the dx. Now this secant x tangent x dx, that's the du, right? That's the part that I want to be the derivative of something. That means that u has to be secant, because the derivative of secant x is secant x tangent x. So I know that u must be secant x, and du must be secant x tangent x dx. Is that all right, everyone? All right, so now what I need to do is see if I can rewrite everything here in terms of tangent, because I have a secant here, that's going to be my u, but now I've got to somehow convert this tangent over. So to convert the tangent, again, I'm going to use the same identity that I had before, but I need to replace tangent with something with secant. So I need to solve this equation for tangent squared. So I'm going to subtract 1 from both sides of that equation. So that is the substitution I'm going to make, the replacement. All right, Varun, are you here?
Yes, sir, I'm here.
Okay, you following okay?
Yeah, I'm trying my best.
Okay, well, if you got a question, let me know.
Sure, of course.
So I'm about to go and try and get all my tangents to switch over to secants.
Okay.
So how can we handle this tangent to the fourth here? How are you going to deal with that?
Would we do the tangent squared x rule where we do secant squared x minus 1 and then square that again? Or-
Yes. So we're going to rewrite that as tangent squared x squared. I'll go ahead and rewrite everything, even though this seems like a pain in the butt to have to do this. Rewriting everything here. The blue, I'm not even worried about the blue because that's my du. I'm not even looking at that. Rewriting tangent to the fourth is tangent squared squared, and then replacing tangent squared with what, Varun?
1 minus, or secant squared x minus 1.
Yeah, so make sure you get the order on that correct. It has to be this way because subtraction is not commutative, right? So you can't switch the order of subtraction. It can change the answer. So there we go. You want to keep going, Varun?
Sure, I can take a stab at it.
Okay, so we have now converted everything that had tangent in it to secant. So I think we're ready. What's the new integral?
So it would be u squared minus 1 squared. And then outside the parentheses, it would be u squared du, right?
There you go. And now, everyone, we're back to a polynomial, right? Now we just expand or do whatever we need to do. I'm going to go ahead and do this all in my head. So I'm going to go ahead and do that in my head, which would be u to the fourth minus 2u plus 1. And then I'm going to hit it with the u squared. So that's going to be u to the sixth minus 2u to the fourth plus u squared. So I'm not showing that work. I'm just going to say dot, dot, dot. I trust that you could get to that. And now term by term integration, just one at a time. And let's let everyone play today. So Nick, is Nick around? Nick, no? Okay, Alex?
Yes.
Oh wait, Nick is here, okay.
Yeah, I'm just having some connection issues right now.
Okay. You want me to come back to you? We'll come back to you. How about Alex?
Which one?
Alex Pohl, sorry. So you.
Can I just say straight to the secant?
Yeah, go ahead.
Okay, so it'd be 1/7 secant to the secant x to the 7th power minus 2/5 secant x to the 5th power plus 1/3 secant to the 3rd power x. My bad. Then plus c.
Yep, good, okay. So Alex went ahead and did the power rule and then just went ahead and plugged all the u's back in. There it is. Okay. All right.
What
Well-
would we do if we had like not just tangent and secant together? What if it was like tangent to the 4th x times sine to cubed x?
Okay, let me preface this with, I'm not sure we'll even be able to do it, but let's just see, okay? You said, what if we had tangent to the 4th x times what?
Sine cubed x.
Sine cubed x. Great question. I'm glad you brought this up because you're actually addressing something I was about to tell you all, which is if you get a trig integral, which this obviously is a trig integral, that does not appear to fit into one of those categories. It's not like sine and cosine, and it's not secant and tangent, right? This is a mixture of the two. The kind of rule of thumb is try and get everything in terms of sine and cosine. So I would rewrite this as sine to the 4th x over cosine to the 4th x, because that's what tangent to the 4th is, right? And then times sine cubed x dx. Then I would probably put the sines together and have sine to the 7th x over cosine to the 4th x dx, right? Now, this is an integral that we have not dealt with. We've dealt with sine and cosine before, but we haven't had, like, they've both been in the numerator, right? They both, like, both the sine and cosine have been up top. We haven't had a fraction out of sine and cosine. But maybe we can do the same sort of thing. Right now, I'm thinking we can peel off a sine. Now, I'm peeling off a sine. Why am I peeling off a sine? Because sine is the derivative of cosine, right? Well, we're off by a negative, but do you agree that I could do that? All right. Now this right here, the sine x dx, is going to be my du, which means I'm going to have to get everything else rewritten in terms of what?
Cosine?
Cosine, right? Everything else is going to have to be rewritten in terms of cosine. So could we do it? Let's see. So I'm going to make a substitution. U is equal to cosine x. The derivative of that is negative sine x. I'm going to go ahead and put the negative on the other side. Please be aware that I did put that negative there, but I moved it over already. Okay, so I know that my du is taken care of, sine x dx is taken care of. I just need everything else in terms of cosine. The denominator already is cosine, right? So I just need to turn the numerator into cosines, if I can. And, you know, I think Christian asked this question, right? Was it you, Christian? Yeah.
Yeah.
Okay, so we got lucky here because sine to the 6th, we can rewrite that as sine squared cubed, right? That's what sine to the 6th is. And then we could rewrite that using the Pythagorean identity as 1 minus cosine squared x cubed. So let's see what happens. The numerator becomes 1 minus cosine squared x cubed over cosine to the 4th x, and then we have sine x dx. Are there any questions? This problem was presented by Christian. It's a great question. I said I don't know if we'll be able to do it. It's looking promising at this point, all right? Because at this point, we can just do a u substitution. So Christian, since you sent us down this road, what would this new integral become?
It would be 1 minus u squared, parentheses to the 3rd power.
Yep.
And then over u to the 4th.
Okay, and then the other part, sine x dx, is actually negative du. So.
Oh, I'm sorry. The negative. Yeah.
Okay. So that's where we'd be, right? And then we have to cube that thing, don't we? Like, let's cube it. Now, the reason I want to cube it is because if we cube it, we're going to have a bunch of terms up top, aren't we? And then we have a single term on the bottom. And so I'll be able to split it into a bunch of separate little integrals and use the power rule on each one, right? So should we do this or not? 1 minus u squared times 1 minus u squared times 1 minus u squared. Whenever I do this, well, there's a way you can do it, a short way is the Pascal's triangle, but I'm gonna do these two first. That's 1 minus 2u squared plus u to the 4th. I like to do that one first, and then I come through and I expand this one out. So I multiply 1 times 1, 1 times that, 1 times that, and then I do that, that, and that. So this will become 1 minus 2u squared plus u to the 4th minus u squared plus 2u to the 4th. Shit, I've lost my spot. Minus u to the 6th, I believe. And then you collect all your like terms. So we should get 1 minus 3u squared plus 3u to the 4th minus u to the 6th. That's just algebra, right, everyone? That's just algebra. Okay, and then over u to the 4th du. I'm going to do one more thing because I don't want to forget this later. I'm going to take that negative out front. I'm going to push it back through. So it's going to make that -1. It's going to make that plus. It's going to make that minus, and it's going to make that plus. And then I don't have to worry about it anymore. And I'm out of room. I'm going to keep going. Now I split this into a couple of integrals. We'll have negative u to the -4. So that was just -1 over u to the 4th. And then I put the u to the 4th back up top. Then I'm going to have plus 3 u to the -2. Then I'm going to have just -3. And then plus u squared. du. Any questions there? And now I can do power rule, right? Should I finish it or just at that point, is everyone good? I don't mind finishing, just let me know. What do you want?
Finish it.
Finish it, finish. Okay, so let's see, hold on, I have to think about this. -3, so 1/3. This will be 1/3 u to the -3. Let me just double check that.
Wouldn't it be a -1/3?
Well, there was a negative already there though, right? Minus 3u to the -1 minus 3u plus 1/3 u cubed plus c. And then you replace all of your u's with Cosine?
I
Forgot.
believe
Was it cosine?
Yeah.
So I would do 1/3, and then I could do cosine x. Now I have to be real careful here because this -3 here, that's a weird notation. In fact, that's dangerous notation. It's probably better to just look at it as to the -3, then -3, and then put cosine x to the -1, and then -3 cosine x, and then plus 1/3, and this one I'll do cosine cubed x plus c. Does anyone have an idea of why I did this notation instead of doing like cosine to the -3x and this one being cosine to the -1x?
Is it so we don't get it confused with like arc cosine?
That's exactly right. There's a very, in mathematics, we have notation, right? And there are a few places in math where our notation just sucks. And inverse trig functions is one of them. And that's because this is not the same as this, right? They don't mean the same thing. This one on the left is the arc cosine function, the inverse cosine function. This right here is the reciprocal. It's 1 over cosine, and 1 over cosine is secant. So this should actually just be secant cubed x, and this one should just be secant x. All right, there it is. So Christian, I hope that that illustrates, you know, that if you do have a problem where you have a mixture of secants and cosines or tangents and sines or something like that, just try and get everything over to sine and cosine and then hope for the best. This one worked. I will say that if you would have changed that problem, if you would have told me in the very beginning, what if we had tangent to the 5th? I think I would have been stuck because I would have had 5th here. And then when I peeled off, or no, yeah, when I got here, I would have had 8 here. And then when I peeled off 1, I would have had 7 here. And this sine to the 7th power, I could not have used the Pythagorean identity on because it's an odd power. So I can't rewrite that. And so I think I would have been stuck at this point. That makes sense? Let me show you all something. Let's go to Wolfram alpha. Why don't I have Wolfram alpha up here? Okay, let's go to Wolfram alpha. And let's ask it to integrate, what was that? Tangent x, oops. What did we just do? The one that Christian gave us was to the
4th.
Right? Times
Sine cubed.
sine x to the 3rd. Let's see its answer. So our answer is going to look wrong, okay? But trust me, they use some identities in here that we didn't use. Like they have cosine 3x. Where the heck did that come from? You know, like they're using some identities. So I still trust that our answer is okay. I don't have any doubt about that. It's just, it's going to look different than the computers. So this answer looks relatively okay, right? Let's see what happens when I change that 4 to a 5. Yeah, okay. That look a little more complicated? That does, right? You've got an inverse hyperbolic tangent function in here. Oh, it's still thinking. Okay. Yeah, so there we go. I mean, that, look at all these cosine 6x. I can't even imagine the identities that were involved in that. Yeah, I know what they did, but you don't need to worry about that. You're not going to have a problem like that. Yeah, so like it's kind of, it's a little depressing when you think about it. I remember when my professor told me this for the first time and I was like, what? If you were to take all the functions out there that exist, okay? Take every function out there that you can actually find an antiderivative of, I mean, or I shouldn't say that. Yeah, let's just say you take every function out there that actually has an antiderivative, because not every function has an antiderivative. Put them all into a big pot, okay? And then close your eyes and reach into the pot and pull out a function. The chance that you can actually find the antiderivative using the methods that you're learning right now is essentially zero. Like, the methods we have are great, but the problems have to be like very specially made for you so that you can do them. If you change one little thing, it can mean you can't do it anymore, which would make you think like, well, then what's the point of all this, right? Like, what's the point if in the real world you have functions that you won't be able to find antiderivatives of? That is going to be the beauty and the power of chapter 8. Chapter 8 is about series. And what we learn in chapter 8, and I don't want to get too ahead of ourselves here because this is getting way ahead of ourselves. What we learn is that if we're given a function, what we can do is convert it into what's called its power series. And then once we have the power series, we can integrate this and we can differentiate this. If we need to take the derivative or the antiderivative, it's super easy to do. It's super, super easy to integrate or differentiate a power series. The question is, how do you convert a function to its power series? And there's a nice formula. And once you know that, I mean, it's pretty awesome because then everything can be done. Like, you can take any function and find the antiderivative of it. I'll give you one more example. There's a famous function. This is like a famous function. E to the negative x squared. No matter what I ever teach you, you'll never be able to find the antiderivative of that. Okay? The antiderivative of that does not exist. All right? However, if you're allowed to do a power series, then you can do it. So I'm going to go to Wolfram alpha and I'm going to type that in. I want to integrate e raised to the negative x squared. And don't think that e to the negative x squared is some special function. You know, like, oh, you know, I heard about this function you can't integrate. There's an infinite number of functions you can't integrate. This is just a good example because it has something to do with standard normal bell curves, but we won't get into that yet. So the answer to this is 1/2 times the square root of pi times ERF. Ooh, what ERF(x)? What's ERF(x)? ERF(x) is an error function. And so basically that's Wolfram alpha telling you that you can't figure it out. All right? Now, if you scroll down in Wolfram alpha, it actually gives you the power series for that function. And then, let's see, yeah, this is just the power series. I'm not sure, I'm thinking to myself. Yeah, that's the antiderivative. That is the antiderivative, but written as a power series instead of as a function. So, moral of the story is just that if you start just off the top of your head giving me functions to do like Christian did, I might get lucky and be able to do it like I just did, or if he changed one thing, we would have been dead in the water. All right? All right, we need to move on. All right, so those examples that I've given you were pretty clean in terms of we could just look at the little, you know, steps and be like, oh yeah, it's even or it's odd and, you know, whatever, and just follow steps. There are other cases which are not as obvious. All right, these cases require maybe identities, some integration by parts, or just some persistence. So we're going to do these 3 problems, and you're going to see they're all very different. And the first one is just, what's the antiderivative of tangent x? Which seems like a very simple question. The antiderivative of tangent. Now we know the derivative of tangent, right? Derivative of tangent is secant squared, but that's not the question. Now I'm going to cheat a little bit here. I'm going to go to the formula sheet. This formula sheet, these are the formula sheets that you're allowed to have on the test. If you look on the antiderivatives page, reference page 6, formula number 12 actually has the antiderivative of tangent. So if you ever were on a test and you had to figure out what the antiderivative of tangent was, you would go to number 12, okay? You would go here. You wouldn't have to show this to me. But I'm going to show you where that formula came from. Why is the answer natural log of secant u? All right, let's do it. So what I'm going to do is first, because I'm kind of stuck to start, right? I don't know where to go with this. I'm going to rewrite it in terms of sine and cosine. That's what tangent is. And then at this point, everyone here, everyone sitting here should be able to do this problem. You have to kind of like go down the right path here. So I'll open this up to everyone. Does anyone have an idea of what we can do? Don't overcomplicate it.
You put it up to
So,
What's that? I didn't hear that.
U substitution?
You sub, Jorge, if you chimed in, I didn't hear you.
I was saying you put up the sine, so it'll be 1 over cosine times sine x, and you take this derivative of cosine, will make negative sine.
Okay, so we can rewrite this like this, and then make a substitution of u being cosine x. And the derivative of that is negative sine x. So again, I'm going to move the negative to the other side already. And so we have sine x dx right there. So this is just a basic u substitution, isn't it? That's all this is? Just a basic u sub. I rewrite this integral as 1 over u times du, but I have a negative, so I'm going to put the negative out front. Any questions? What's the antiderivative of 1 over u?
Absolute value, ln, absolute value.
ln absolute value of u plus c. Okay, what was u? Cosine, right? So this is going to be negative natural log of the absolute value of cosine of x plus c. Now, does that match the answer that they had in the formulas? It doesn't, right? The answer they had was this. So did we mess up?
Yeah.
So go back and think about algebra, okay? College algebra. Do you remember learning about properties of logs? Do you remember this property? If you have the natural log of x to a power, let's just call it p, that the p can come out front in front of the natural log? Remember that property? Well, that property goes the other way too. If you have a number out front, you can move it up as a power. So if we realize with our answer, that's a -1 out front, we can move that up as a power on the cosine. So we can rewrite this as natural log absolute value of cosine x to the -1. But then what is cosine x to the -1 really mean?
secant.
Yeah. So it's the same answer. So on a test, you know, if you had written negative natural log of cosine x, I would be happy with that. That's no problem. Okay, you ready for the next one? Okay, would y'all agree that I did not have to go look at that, I didn't have to go look at these steps, right? I didn't need these at all? Where's my mouse? There it is. Come here, where are you? So I did not need that. For this problem, I did not need this at all. Okay, next problem. Okay, we're gonna do a little Jeopardy, final Jeopardy, where you get like a minute to think about how you might want to approach this. And then we'll ask the class. I'm gonna go refill my drink. I'll be right back. Jeopardy is over. Okay, I don't expect that anybody got this. So does anyone want to tell me at least what they tried to do?
I tried writing it, writing it as 1 over cosine x times 1 dx,
Yep.
and then did like a u substitution with 1 dx, and then got, or just at 1, and then got du equals dx. That's where I got stuck.
Wait, you let u be what?
Just 1.
Okay, well, if you do that, then du is not dx. Du would be 0 dx, because the derivative of 1 would be 0. So that's not going to work. Maybe someone tried cosine x here, and derivative is negative sine x dx. But the problem there is you don't have it. You don't have sine anywhere, right? Anyone try anything else?
I tried integration by parts.
Okay, so what did your table look like?
I made u equal to secant x,
Okay.
and then the derivative would just be secant x tangent x of u. And then I just made dv equal the 1 dx.
Yeah. And then the antiderivative there, that should be a v here, sorry. The v would just be x then, right?
Yeah.
And so that, I mean, that table actually, you can generate the table, right? I mean, that's okay. The problem is ultraviolet minus voodoo looks like this. Here's what voodoo is. Voodoo is x, secant x, tangent x, dx. And unfortunately, that x in front is complicating things now because it's no longer a trig integral. It's a trig mixed with a linear expression. So that's going to be a difficult, we're pretty much going to be stuck at that point, all right? So I didn't expect anyone to get this because I would never have gotten it either. Like, as a student of this subject, this is an example of a problem where I'm going to show you how to do it, and we're going to just appreciate and applaud the person who spent probably months, if not years, trying to figure out how to do this, all right? So someone figured this out. They don't get any recognition for it. I don't even know who did. Even though it's awesome, it's not worthy of being put in any book or anything like that. So it's a very elegant, simple solution, but it's, how did this person come up with this? That's the question. So here's what whoever figured this out, here's what they did. They said, all right, I'm going to take this secant x, and I'm going to multiply it times 1, all right? But the one that they picked was just super, super clever, all right? Here it is. They picked this for 1. Secant x plus tangent x over itself. Secant x plus tangent x dx. All right, now why in the world is that a good thing? Let's see. Let's distribute the secant through the top. And you're going to look at that and you're like, how in the hell is that better than what we started with, right? Let's see if anyone sees it.
You could take the, you could use one of the rules you learned, I think, Monday.
Okay, so like, you know,
I mean,
like if you have tangents and secants together, is that what you're saying?
Yeah.
That I would say would look promising, except that we got additions between these things. So we can't peel things off like we did before because we don't have like factors. We have addition and subtraction, so we have terms. So it's not going to work the same way. I'll give you a hint. It's not even that complicated.
can't you just cancel out them?
If you cancel things, you're going to go back to secant x.
Can we put a secant x squared over secant tan secant
Like
x
split
plus
it into two.
tan x.
You could do that. You could split it in two, but it's not even that much. You don't even need to do that much. It's like right here under your nose, like it's right there. You just have to see it.
Couldn't you use one of the identities for secant squared x? You can use like the 1 minus tangent one, then convert secant tangent x to something else, maybe?
Yeah, so maybe you can do something with the secant squared, use the Pythagorean identity, turn it into 1 plus tangent squared, and then do something. Yeah, I mean, you might be able to go that way, but it's not even, you don't even need an identity.
Could you just peel off the entire numerator and then just have secant x plus tangent x over, or with a -1 exponent?
You could do that. I'm going to write it like this, because I think if I write it like this, you might be able to see it better. No? Basic U sub. Just a basic.
Oh, you make u equal to secant. And then you can get rid of the secant x tangent x.
Almost. You said let U be the secant x?
Yeah. Oh, the entire denominator.
The entire denominator. What's the derivative of that? Well, you do them separately, don't you? So what's the derivative of secant x? Secant x tangent x. Derivative tangent x. Secant squared x, right? And that's exactly what you have. You have, that right there is the derivative of the yellow. Exactly. I mean, it's flipped, the order's flipped, but that doesn't matter. So I can rewrite this. Let me just substitute. U is going to be the entire bottom. And then du is secant x. Go ahead. So that means this integral just becomes integral 1 over u du. And the antiderivative of that is natural log of u, absolute value of u plus c. And what was u? U was secant x plus tangent x. So we'll just plug that in right there. And if you look on your formula sheets, I'll bring them up in just a second. I know some of you are still writing. If you look on your formula sheets, the antiderivative of secant x is the natural log of secant x plus tangent x, or the natural log of the absolute value of secant x plus tangent x. So how about that? What do y'all think of that? That one, huh? It works, right? But why? Like, how did that person come up with that? Persistence, I guess. That's what math majors have to deal with. That's the type of world that math majors live in, is where you have to come up with these things that are not obvious, but they work. And then you can share that with other people. Okay, any questions? I'm gonna move on to the next one. We have one more to do. All right, the last one we're doing is secant cubed x. Now this one does not require any magical one that you have to like come up with. Everyone in this class should be, well, everyone in this class has seen the techniques and tactics on how to go about this. It's just a matter of going down the right road here. So anyone have like just an instinct as to what you might want to do on this?
Do you peel off a secant x?
Okay, I'll peel off a secant x. Is it all right if I peel the secant x off the front? It doesn't matter which way I write it, right? I could go secant x times secant squared, or I could do secant squared times secant. It's kind of up to you. I'll write it both ways. Just, I don't want to force anybody down a particular path here. Okay, that is a legal move, right? Everyone agree that that's legal? Now, I'm not even saying that this is the right way. I'm just saying that that is a legal move. So I have no problem with that. Okay, what now?
I think what you can do is use the identity on the secant squared x and turn that into the, what was it, 1 plus tangent x squared?
Okay.
And
So-
then after that, I forgot if what secant is the inverse of, isn't it like inverse of cosine or something like that? So wouldn't you be able to turn all of that in terms of cosine?
Yeah, so let me write that. So this is, Peggy's gonna go down this road, right? Everyone agree that that's a legitimate move? Secant squared, the identity is 1 plus tangent squared. And then you wanted to rewrite that secant as 1 over cosine?
Well, actually, now that I think about it, I don't think it'll work.
Why?
I don't know, because I realize the 1 plus tangent is kind of locked. So I guess, well, you could turn it into 1 plus, like, sine squared x over cosine squared x, like the tangent, and then turn the secant into 1 over cosine, so it's all in one term and not, like, 2. But I don't know if that'll work.
Okay. Everything that you said is legal. Like, that's all legitimate algebra. Did you want me to do anything else?
No, I have no idea.
No?
Yeah, I have no idea what to do now.
Yeah. So I think if you ever get to a point like that where you're on a test and you're just like, I don't know, you might just want to kind of reevaluate, start over, maybe do something different. But everything you did is right. Like, there's nothing wrong with what you done at this point. Okay? There's nothing wrong. Everything is algebraically correct. It's just, is that going to get you to the end? I like to make an analogy. I don't think I've talked to you all about this. You know, you're trying to get from point A to point B. Have we talked about that? You know, like all these problems, you're trying to get from the beginning to the end, right? Trying to find the antiderivative. And when I'm sitting here and I'm showing you the problem and I'm doing the problem, you know, with my experience in this, I can show you a relatively short path to the answer because I know every turn to make, I know which way to go. And so it looks like it works out smoothly. What Peggy was doing just now is she's on a road, okay? Now, whether or not that road is leading straight to the answer, we don't know yet. But it's a road. She has not broken any algebraic, you know, she hasn't done anything illegal. She hasn't, you know, and we don't know if she's going to get there, maybe not, I don't know. And then she might just wind up saying, you know what, screw this, right? Like, I need to start over. As long as you don't do anything illegal algebraically, then you're on a road. So I think that's one of the biggest challenges in class like this is just trying to figure out if you can find the path from A to B. Because you can oftentimes find yourself on this long journey and realize, you know, I don't feel like I'm getting anywhere, you know, going around in circles. All right, so Peggy, are you kind of putting up the white flag for now?
Yeah.
Okay. So what would, I'm going to stick with you, Peggy. If that didn't work, if turning the secant squared into 1 plus tangent squared didn't work, what other things do you think you might be able to throw at this then?
I have no idea then.
Okay, so what are some of the things you've learned in this class? What are some of the techniques? Right, basic use of, right? What else?
I don't know the voodoo one, but that's not going to work here.
Why not?
It just doesn't seem like it's going to work.
Doesn't seem like it. Okay, so if it doesn't seem like it is, that doesn't, you shouldn't turn away from it though, because maybe it will. Maybe it doesn't appear to you that it's going to work initially, but it might still. So you always want to be willing to put that on the table and try it, because you might be surprised by, oh wow, this is going to work, you know. So Peggy, let's go with that. I'm gonna force Peggy through this, down this path, okay? Because I think this will be constructive for everyone in the class. Peggy did not believe in the integration by parts as being an option, but I'm forcing her this way. Okay, Peggy, you have to pick, and I hope you don't mind, I'm not picking on you, right? You understand that? You're okay?
I don't know what to do, so can you just pick someone else?
You agree with the table, Peggy?
Yeah, I'm just really tired. I can't really think straight, so.
Okay, all right. Then I'll ask you one more question. I'll leave you alone, I promise. Promise. There's two things here. You've got to pick one of them for U and one of them for DV. I would recommend you look at the DV part first. What would you rather find the antiderivative of? Secant squared or secant?
Secant squared.
That's right, because the antiderivative of that is tangent. Good job, okay? So I think it's a natural place to stick the secant squared x here. And then here, secant x, well, that we can differentiate, can't we? We can differentiate that. Okay, so let's go down this road. We're in it now. We're going to du here, derivative of secant x is secant x tangent x dx. Had anyone started this already? Had anyone started to go down this road? No, not yet. Okay.
I did, but I kept it as secant cubed x.
Okay, so you use that as your u?
Yeah.
And then had chain rule? Oh yeah, that's going to get ugly. Yeah. Okay, so let's go with this. This is going to become, okay, so we're going from here. We're ready for ultraviolet minus the integral of voodoo. So ultraviolet would be secant x tangent x minus the integral of voodoo. Now look at voodoo. It's secant x times tangent x again. So I'm going to put tangent squared x dx. Any questions on that? Do our steps deal with this? Do our steps deal with this? Where are our steps? Where are they? If we have an even secant power or an odd tangent power, we don't have an even secant power and we don't have an odd tangent power. So unfortunately, our steps don't help us here. Okay, well, this is the last problem of the section, of this part of the section. So of course it's going to be a little bit more challenging. So we've gotten here. I'm ready to take any suggestions to move forward on this. I'll give you a slight hint. I'm going to put the original problem. Here's the original integral, and we're saying it's equal to that. Right? That's the original problem. Secant cubed x dx is equal to that.
Would we be able to rewrite the tangent as in secant squared x minus 1 and then distribute the secant x?
Absolutely. And if you did that, wouldn't you get a secant cubed somewhere?
Yeah.
So the original integral that you're actually looking for is going to appear again on the right-hand side. Let's write that down. We are going, the original integral is this, is equal to secant x tangent x minus the integral of secant x, and then we're rewriting tangent squared x using the Pythagorean identity. So you have to go back and look at the Pythagorean identity. You would have to move the 1 to the other side, so it becomes secant squared x minus 1 dx. And so what Christian, I think, was kind of seeing was that if the tangent squared x became this thing, then when we do this distribution right there, we're going to get a secant cubed. And that's the original integral. And so maybe we'll be able to move that back to the other side. We've done something like this before, haven't we? There's been some problems where this has happened, where the thing we're looking for appears on the right and then we can move it over. So we have to distribute both though. So I'm going to go ahead and do that. I'm also going to do one more thing here. Hopefully you recognize what I'm doing. Instead of having one integral with two things in it, I split that into two integrals. So on my first distribution, I'm going to get a secant cubed. And so that's my first integral. And on the second distribution, I'm going to get a minus secant. But don't forget there was a negative out front. And so that negative is going to turn it into a plus. So I have two new integrals. Are you happy with that? Or not happy? Are you okay with that? Any questions on what I did? Do we know the answer to this integral in yellow? We just did that problem. That was the magical one, right? So we know the answer to that. This integral in blue with the little minus in front of it, that's the original integral. So I'm going to add it to both sides of the equation. When I add it to both sides, it'll go away on the right, it'll appear on the left. So I'm going to add this integral to both sides. And on the right side, it goes away. On the left side, how many of those integrals do I have now?
Two.
Two of them. So I have two of these integrals that are equal to secant x, tangent x, and then that stuff went away, and I still needed to find the yellow part, which we did in the previous problem, so that turned out to be plus the natural log of the absolute value of secant x plus tangent x. I never showed that to you on the formula sheet, did I? But it's there, you can look at it. So this goes to this. And that's it. We just have one more thing to do. What do we do?
Divide both sides.
Okay, divide both sides by 2. Okay, so get rid of the 2. I'm just going to put a 1/2 in front of that, 1/2 in front of that. And that's our answer. That's a little tricky, huh? Okay. So at this point with your homework, you should be able to at least attempt to do in theory here, you should be able to attempt the first 36 problems. Like, you know, start with the odds, do what you can. And make sure you go through my homework solution videos if you get stuck, right? And there's still a lot to learn, okay, when you go through the homework. Still a lot of examples that I didn't give you exactly the same thing, and so you're gonna have to work through these on your own. And, you know, there's a saying that, I don't know if I told you when I was in my 20s, late 20s, early 30s, I was doing a lot of triathlons and things like that, and riding my bike a lot. And there's a saying in the cycling world that when you're on a bike and you're going on a really long ride and you're suffering, right? You're sitting there suffering on the ride, that you're putting suffering money like into the bank. Like the suffering is you making deposits into this bank of suffering. And then later on when you're in competition and you're sitting there and you're trying to do well, you can withdraw money from that bank. Like the suffering is for a reason. It's for later. So what I'm getting is the homework is suffering, all right? It's going to be some suffering, but that should pay off during the exam. All right, during the exam, you will be able to withdraw from that knowledge that you've gained, and you'll be able to hopefully get through those problems on the exam. I'm terrible with analogies. That's the best I can do, okay? All right, we are ready to move on just to the second half of this section, though. We're still in 6.2, all right? So 6.2 has another part to it. and it's called trigonometric substitutions. So let's read this. After we master the above concepts, okay, so we are now going on the assumption that you're very comfortable with trig integrals. You can do, you know, sine, cosine, different powers, mixtures of tangent and secant. You've gotten really good at this. You have suffered through the work, right? We can use that knowledge along with a very interesting type of substitution to find the antiderivatives of some really complicated functions. So we are going to do a new type of substitution. And when we do it, we're going to wind up with a trig integral. And then we're just going to do what we just did. All right? So the beginning of these problems isn't going to look like anything that we've been doing. But we're going to transform the problem into something that we've been doing, like trig stuff. All right? So I'm going to get to it now. And I'm going to lead us to it. I'm going to try and build up to this. All right, so right now, just in your minds, I want you to completely erase the idea that we're trying to do antiderivatives. All right, just don't even think about antiderivatives right now. Just think about algebra, just algebra. So I'm going to write down an expression. This is a square root expression, and we're going to be focusing only on square root expressions for the rest of this section. If I have a square root expression, and inside of it, I have something like 9 minus x squared. All right. We all know, or else we wouldn't have passed the algebra. We all know that this is not the square root of 3 minus x, right? You cannot just do the square root of each one. That's illegal. So that's not true. So if I wanted to simplify this, I really can't do anything here, right? I mean, there's nothing really more that I could do. I could do this. I could rewrite the inside as 3 plus x, 3 minus x, like a difference of squares. But still, at that point, you can't really do anything with that, right? So I'm going to do something. I'm going to make a substitution. And it's not going to seem like I should be doing this, but I just want you to follow me through it. I'm going to let x be something, right? I want everyone here to replace the x with something. And here's what I want you to replace it with. 3 sine theta. And you're gonna be like, what? Like, why 3 sine theta? Okay, well, just bear with me, okay? Bear with me. Let's see what happens. So in the expression, we have x squared, don't we? Let's see what x squared would be for us. X squared for us would be just us squaring both sides. So you square the left, you get x squared. You square the right, you get 9 sine squared theta. Y'all agree? Okay, now, what would this expression then, what would this turn out to be, this big ugly thing? What would it turn out to be if I go ahead and make this substitution? I have the 9 that's there, right? And I'm subtracting from that x squared, but I just said x squared was 9 minus sine squared theta, right? So I'm going to put that in here, 9 minus sine squared theta. Notice that they both have 9s. That was by design. I intentionally made that. I made that a 3 so that when I squared it, it would give me a 9. So that was intentional. Since they both have a 9, I can factor a 9 out of both of them, and that will leave me with a 1 minus sine squared theta. And what is 1 minus sine squared theta?
Cosine squared.
Cosine squared theta, Pythagorean identity, right? If you use the Pythagorean identity, that's just cosine squared theta. So this becomes the square root of 9 cosine squared theta. And now what I've done is I've taken this minus that was there that we couldn't split this into 2 roots or anything, and I've gotten rid of it. Now I've got multiplication. So I can just take the square root of each of those. And the square root of 9 is 3. And the square root of cosine squared is cosine. So this expression turns into that expression if I make this substitution, right? If I make that substitution, then this radical expression will convert into a trig expression that's pretty nice. Now, at this point, imagine that there was an integral. Would you rather find the antiderivative of that, or would you rather find the antiderivative of cosine? Right? Like, I would rather do cosine. I know the antiderivative of cosine and sine. So it looks like this sort of substitution is just there to help us. It's not a natural substitution, not something that you would just be like, oh yeah, let's just do that. But it's been figured out that if we do it, it works, okay? So in general, here's what we have. Generally speaking, if we have a square root, and we've got some number here, I'm gonna write a squared minus x squared. And next to this, I will put the problem we just did. We had square root of 9 minus x squared. So all you have to do is realize that this right here is some number squared. What number squared is that? 9 is what number squared? 3, right? So that's 3 squared. So if we ever see this, a squared minus x squared, then if we make the substitution, then if we let x be equal to a sine of theta, then what does this expression turn into? What will it turn into? A squared minus, well, what would x squared be? A squared sine squared. So we take that and replace the x squared with that. So we get a squared sine squared. And then that a squared can be factored out of both, right? The 1 minus sine squared theta will always turn into cosine squared theta. And now you can take the square root of both. Let me recap. If we ever see a radical expression where we have a constant squared minus our variable squared, then if we make the substitution that x is equal to a sine theta, then we can guarantee ourselves that this expression will turn into a cosine theta. Every time. Every single time. So let's see if you understand this. What if we have square root of 25 minus x squared? What would our substitution be?
5 sine theta.
Our substitution would be x is equal to 5 sine theta. Okay, and then what does this root turn into? Without going through all the work and factoring things out, and just what do you know that's going to turn into?
5 cosine theta.
5 cosine theta. Is that clear, everyone? Every single time. What about this one? What if we have square root of 3 minus x squared? Then what's the substitution? This one's a little tricky because I've been giving you perfect squares, haven't I? 9, 25.
Would it just be root 3 sine theta?
Yeah, so we have to pay attention to the fact that when you look at 3, right, we're saying that's a squared. So a squared is 3, right? Take the square root on both sides. That means a is the square root of 3. Now, we don't know what the square root of 3 is, right? It's some decimal, but that's a, right? So we're going to make the substitution root 3 sine theta. And so what does all of this nasty, ugly root turn into? Without doing any work, root 3 cosine theta, right? That's what it's going to become. So I'm going to bring up our formula sheets real quick. And I want to point this out, all right? Right here, it says, what if you have this expression, a squared minus x squared? Now remember that you can have this on your test, right? Then it's telling you what substitution to make, a sine theta. Now, what this formula sheet does not tell you is what the ugly root turns into, right? A cosine theta. I'm going to allow you right now to add that to this. You can write A cosine theta there. You're welcome. All right. That root expression will become A cosine theta. All right. Now, what if our expression was different? What if we had this instead? My first example was 9 minus x squared. What if we have x squared minus 9? Well, that's not the same thing, right? 9 minus x squared is not the same as x squared minus 9. So I'm again going to suggest that we make a substitution. But the substitution that I'm going to use is not the same substitution. It's not A sine theta. It's actually going to be A secant theta. Now let's see why this works. What would this turn into if we replace the x? Oh, sorry, we have to square it. Let's square it. This becomes 9 secant squared theta. So if we replace the x squared with that, we get 9 secant squared theta minus 9. Again, we can factor 9 out. And now we have secant squared theta minus 1. And what is secant squared theta minus 1? According to the Pythagorean identities, that's just what?
Tangent squared.
Tangent squared. And now we can take the square root of each one, so you get 3 tan theta. And this would work for any number we have here, right? So this is now like our a squared. So it's the same formula we had before, but they're reversed, aren't they? They're like switched around. And if they're switched around, we do a different substitution and we get a different result at the end. So we go back to our formula sheets and we look at that. I'm now talking about this scenario on the bottom here. If we have x squared minus a squared, the substitution we make is a secant theta. And what will this turn out to be? This is the part you can add to your formula sheet. That will turn out to be what? A
Tangent
what
theta.
was it? And theta. Every single time. And then we have one more that we can do. Right? We have another one. What if there's a plus sign between them? So if there's a plus sign between them, we will make the substitution x is equal to a tangent theta. And I'm not going to work through this one. You're just going to have to trust me on this. That what comes out of this is a secant theta. So you can add those three things in red to your formula sheet now. All right, you ready? We have just enough time to do one problem. And the first one I'm going to do is this one. Integral x cubed times the square root of 16 minus x squared. So you might look at that initially and be like, okay, hey, wait, you know, basic u sub, maybe basic u sub, because if you let u be x cubed, the derivative of that's x squared, but that x squared is trapped under a root, right? You don't want that derivative to be trapped. So that won't work. Maybe you're thinking integration by parts. I don't know about that. That seems like that might get ugly. But here's the thing that should be kind of making light bulbs go off in your mind. You see the square root, right? You see something squared minus something squared. So you're seeing that form, right? You're seeing in this, what's in this formula sheet, you're seeing one of these forms, right? Which one, which form are we seeing? The top one, middle one, bottom one?
Top one.
Top one, right? So it's a squared minus x squared. So what we know is that we should be able to make a trigonometric substitution. The trigonometric substitution we're going to make is that x is going to be a sine theta. So for us, that's 4 sine theta. What do we know the square root? I'm going to write it down here on purpose. What do we know the square root of 16 minus x squared is going to turn into without having to do all the work? We know
4
that
cosine
become
theta.
4 cosine theta, right? So right now, as it sits, this whole root thing, all of that root thing, can be replaced with 4 cosine theta. The x we have here can be replaced with 4 sine theta. Now we still have to cube it, don't we? Don't forget we have to cube that x. What's the one thing I have not messed with? Because I've got x's, but I'm replacing things that have thetas in them. What have I not resolved?
dx.
Dx. Okay, so this is the one part we haven't discussed. How are we going to resolve the dx? Well, what we're going to do is we're going to go back over here to this equation, and we're going to do dx d theta, take the derivative on both sides of this equation right here. So what is the derivative of 4 sine theta? Well, just 4 cosine theta, right? Pretty clean there. And then I'm going to move the d theta to the other side. I don't want it down here. So now I know what I'm going to replace dx with. Dx is going to be replaced with that. So I am now going to rewrite the whole integral, and it's going to be in terms of theta. Integral. Okay, x cubed means I need to take 4 sine theta and cube it. The blue part, the square root stuff, is all just turning into 4 cosine theta. And the dx is turning into 4 cosine theta, d theta. And now we have a brand new integral. It's all in terms of theta, and it's a trig integral, right? It's a bunch of trig stuff. So I'm going to go ahead and do this. I'm going to take all the 4's out of the integral. And all those 4's, we can multiply that. It's 4 times 4 times 4, 5 times. I could do that. I'm not worried about it. And then I have sine cubed theta. That's because I cubed the 4 and I cubed the sine to get it out of that parentheses. And then I have cosine squared theta, d theta. All right, let's take a breath. Are we good up to this point? We're at a trig integral now. How do we deal with this trig integral? We go look at our little cheat sheet. We have an odd power of sine. And since we have an odd power of sine, we should be able to peel a sine off. So this becomes 4 to the 5th integral. I'm going to peel off a sine, so I now have sine squared theta. I still have a cosine squared theta. I'm peeling off that single sine. Here it is, sine theta d theta. So now what I know is that my sine theta d theta, that's my du. So what's the u?
Cosine.
Cosine. And we're going to be off by a sign here because du, we're going to have a negative that we're going to have to move over to the other side. So what I need to do now is get everything here on the left that's not blue, everything there written in terms of cosine. Well, that means all I need to do is deal with that sine squared. But oh, sine squared is 1 minus cosine squared. Any questions? Sine squared became 1 minus cosine squared. Everything else just kind of stayed. Now what?
Replace cosine with u, and then
Cosine with u,
yeah, just make sine theta d theta equal to du.
du, and negative, right? We'll put the negative. So 1 minus u squared, and then we've got u squared, and then I'll go ahead and just do it here, negative du. And then this will become 4 to the 5th integral u squared minus u to the 4th. I still have times negative du. I didn't pull the negative way out in front this time, did I? I could have. I chose to leave it there because I'm going to actually distribute it through right here, right now. So this is going to become 4 to the 5th integral, and that's become minus u squared plus u to the 4th, right? Minus u squared plus u to the 4th. So I'm going to write it this way. U to the 4th minus u squared, which is the same thing, just written backwards. Now antiderivative. One-fifth u to the 5th minus 1/3 u to the 3rd plus c. We made it. Not yet. Why are we not there?
We had to distribute the 4 to the 5th power.
We could distribute the 4 to the 5th.
Oh, and convert the u's back into.
Okay, so u's got to go back to what it was, right? What was u? Cosine theta, right? Cosine theta? Okay, so this has got to become 4 to the 5th. I'm going to leave it in here for now. This is 1/5 times cosine to the 5th theta minus 1/3 cosine to the 3rd theta plus c. Okay, now are we done? Why aren't we done?
Gotta distribute.
We could distribute it, yeah, but that's not it. We're still not done. What is our answer in terms of?
Oh, it's in terms of x.
Our answer right now is in terms of theta, right?
Yeah.
Original problem way up here was in terms of x. We've got to get everything back to x. So how are we going to get this back to x? How do we get this to have x's in it again? Let me show you how. You go back to your first trigonometric substitution, x equals 4 sine theta, and you write it down here on the side. Then you isolate the trig function. And then you draw a reference triangle. We did this in the beginning of this class. Do you remember at the very beginning I said we're going to do a reference triangle that's going to come up later? Well, later is today. So from that relationship, we know that if this is theta, sine is opposite over hypotenuse. That means this side is x and this side is 4. And if you have two sides of a right triangle, you can always solve for the third. And I'm going to trust that all of you could solve this side right here, 16 minus x squared. Square root of 16 minus x squared. This you have to solve for. That was not given to us. We have to solve this. Because we knew what this was, we knew what this was. Now, according to that triangle, do you know what cosine of theta is?
Square root of 16 minus x squared over 4.
That's right. It's the adjacent over the hypotenuse. So now what I can do, and I'm like so almost out of time, I can come in here and I can replace all my cosine thetas with this fraction, square root of 16 minus x squared over 4, that's cosine theta, all to the 5th, minus 1/3, and then square root of 16 minus x squared over 4, all to the 3rd, and then plus c. Y'all see where that came from? Jeez. Okay, I'm going to clean this up. This is a mess. I'm out of time. If you need to go, go. But I'm going to finish it. 1/5. Okay, I'm going to rewrite this as 16 minus x squared to the 5/2 over 4 to the 5th. So all I did there was I applied the 5 to both this top and this bottom. And because 16 minus x squared is under a square root, that's the same as raising it to the 1/2 power. So if you take something to the 1/2 power and raise it to the 5th power, you multiply 1/2 times the 5th, or 1/2 times 5 becomes 5/2. Do the same thing on the other one. This will become 3/2, and on the bottom it's just 4 cubed plus c. And the reason I wanted to clean that up is because now I can distribute this 4 to the 5th through here and here. And I hope that you see when I do this first one, the 4 to the 5ths just go away. So that leaves me with 1/5, 16 minus x squared to the 5/2. And then when I do it the second time through, 3 of the 4s cancel, but I still have 2 4s on top. So that's going to be 4 times 4 is 16. So I'm going to get 16/3. 16 minus x squared to the 3/2 plus c. That is my antiderivative. What do you think?
Would we need to do all that for a test?
Absolutely.
That's a lot.
Yeah. Yeah. So look, when we start talking about, integration, so we're going to learn like, just power rule, then we're going to do like basic U sub, then we're going to do integration by parts, then we're going to do trig integrals, then we're going to do trig sub, and then we're going to do partial fraction decomposition. We are at the last 2 methods right now. And these are by far going to be the hardest. Because look, we used everything in this problem, right? We pretty much used everything. I mean, we did our trig sub. Once we had our trig sub, we did our trig integral. In the trig integral, we did a U sub. Within the U sub, we did power rule. Then we had to switch everything back to trig stuff. Then we had to use reference triangles to come back to x, and then just do some algebraic simplification. So it's like one problem that encompasses multiple ideas. So, you hear about these classes that are like capstone classes that kind of end your exposure to something. These problems are like capstone problems. Like if you can do a trig sub problem, then you've demonstrated that you can do a lot of the things you need in order to do integration. In fact, I'll show you what I showed my other class. I know it's time to go. This is the first problem of the test, a test I gave a year ago. That's the first problem on exam 2. Okay, so look, what you'll notice there is that there's no, like I didn't start the test with a trig integral, right? I started the test with a trig sub. Because if you're going to do a trig sub, you've got to be able to do a trig integral. So it's kind of like killing 4 birds with 1 stone, right? Like that problem is going to make sure like everything's going to be covered in that, right? And then the next problem isn't even a trig sub, it's partial fractions. So I've already moved on to the next section. And you might imagine that that problem right there has a bunch of stuff built into it also. So there's not a whole lot of problems. How many problems do I have on this test? 6 problems on that test. So I'm offering to you right now, or not offering, I'm asking you for this to be your first quiz, right? This right here. So next time we meet, what I want you to do is go through, even though I've only done 1 example, I want you to see if you can do that problem. It's trig sub. See if you can make the correct substitution. Then after you do the substitution, you have a trig integral. Evaluate that trig integral and just see how far you can get. I think you're going to get stuck at some point, but see how far you can get and have that work like in front of you next time we meet. If you don't finish the problem, that's okay. I just want to see that you at least did the trig sub, got it to a trig integral, and evaluated the trig integral. So comparing to what we just did, I would expect that everyone would get, on that problem that I showed you, everyone would get at least to this part right there, where you've got an answer in terms of theta. Getting it back to x is going to be hard. Not hard, but we haven't talked about it, so you might have trouble with it, all right? But let's make that our first quiz grade. And yeah, okay. Your homework is to make sure you can do the trig integrals. That's your homework. You don't have to start the trig sub yet. We're going to come back. I'm going to do more examples of trig sub so we can get into all the little finer details of things. And then at that point, we'll be ready to move into partial fractions. And then we'll almost be done with integration. We can move on to applications and things like that. All right, today was a big day. Next class will be a big day too. Also, trig sub. Y'all happy? Have a good day.
Thank you, Professor.
See you later,
Thank
sir.
you.
Have a good day.
Thank you. Have a good day. I'll hang out here if anyone has any questions.
Your office hours start at 1, right?
At 1 o'clock, yep. I'm gonna just step
Okay.
out for a minute and I'll be right back.
It's just in this room?
No, it's a different session. So
Okay.
go to the syllabus and I think there's links on the syllabus there.
Okay, cool.
Okay, all right. I'll see you in a
All
little
right.
bit.